All right, so we should be good to go. Hi, everyone. Thanks for joining. Kamiel Janssens from the University of Adelaide, who's a collaborator on SABRE, has agreed to give us a seminar today on his work during his PhD, which was at the University of Antwerp and Côte d'Azur. So please take it away.
Thank you very much. Okay, perfect. So I will talking a bit about my PhD project, and I will highlighting how I try to understand a little bit more of the fundaments of the universe by listening to the symphony of gravitational waves or the gravitational wave background. Okay, so I did my bachelor's and master's at the University of Antwerp in Belgium on electroweak interactions with CMS. Then I did a joint PhD at the University of Antwerp and Université Côte d'Azur in Nice in the south of France on gravitational waves with a specific focus on data quality for gravitational wave background with Earth-based detectors, so LIGO, Virgo, CAGRA, and also the Planck's Einstein telescope. And so as of half a year or so, I'm now doing a postdoc on SABRE with direct detection dark matter, with a focus on optical simulations and PMT calibration at the University of Antwerp. So what I will be discussing today is what is the gravitational wave background and why should we care trying to measure it. A little bit of focus on Earth-based detectors, as that was the main focus of my work, but I will briefly mention pulsar timing arrays because they had some very exciting news in the recent year. Why we want to use correlation techniques and how noise can haunt us there and be not so pleasant for our analysis. And then I will use magnetic noise as a showcase how it can impact Earth-based detectors. Some other work I did but will not cover is how correlated seismic noise for closely located detectors such as the Einstein telescope can be an additional nuisance. Some of the methods I worked on, how we can try to deal with those noise sources. And then on my spare time, I also was involved in a survey for the mental well-being in gravitational waves and high energy astrophysics. The gravitational wave background is a superposition of many weak either astrophysical or cosmological sources, and we characterize it best statistically. It's very similar to the CMB, but then rather from light sources, from gravitational wave sources. And so the signal typically contains information about the distant universe. And so what we are trying to measure is the energy density stored in these gravitational waves. And we're trying to measure it over a huge range of frequencies where Earth-based detectors are lying here in the couple of hertz to kilohertz range. And then future space missions such as LISA is measuring in the millihertz region. And then pulsar timing arrays, which I will talk about later as well, is in the nanohertz region. To kind of get a sense of how small the limits are, which we are already placing on the gravitational wave background, which is on the order of 10 to the minus 9. We all know matter is about 5% of the energy density of the universe, dark matter 25%, dark energy 75%. The CMB is about 0.005%, and even though it's a tiny contribution, it contains a lot of information about the early universe, and to some extent revolutionized our knowledge of the universe. And so the idea and hope is also that this will be the case for the gravitational wave background, even though it's extremely tiny, and we haven't observed it yet. Pulsar timings array are very close, I think. It can contain a lot of information, both about distant astrophysical processes, but also cosmological phenomena in the early universe. And so that makes it quite interesting to look at. With now switching to the dark matter field, made me realize there are quite some connections between the two fields, because there are definitely some models of dark matter which would leave an imprint on a gravitational wave background. Some particle-like sources would be cosmic strings, which can, when they collide, create gravitational waves, or also some axion models. One non-particle-like dark matter candidate, which with the increase of gravitational wave observations has again gained some more interest, is primordial black holes. If there would be a vast majority of tiny primordial black holes on the order of fractions of the mass of the sun, this could contribute to this open debate as well. So on Earth, there is a network of multiple gravitational wave detectors, of which 3 have been sensitive enough in the past to observe gravitational waves, 2 in the US, like Hanford and Livingston, and 1 in Europe, Virgo, and then CAGRA is nearing its potential to contribute significantly to future observations as well. And so as a gravitational wave passes, the interferometer arms, because all of them are laser interferometers, so you have an L-shaped detector of about 4 kilometers. And if you have, for instance, 2 black holes orbiting around each other and emitting gravitational waves, they will cause tiny ripples compressing and stretching out the fabric of space-time. And this will leave an imprint, which you can see in your diffraction pattern of your laser detector. And I stole this slide from quite some time ago, where it was still 100 detections, but now with a recent 04 observing run, they're well going past that. And I think now they're around 2 or 3 observations every week. So the number is rapidly climbing into the hundreds. So what about pulsar timing arrays? So instead of having a laser arm on Earth of a couple of kilometers, you use 2 pulsars as kind of the end of your laser arm, and you construct an interferometer in that sense. But instead of just 2, you have hundreds of them, but you have other noise sources to worry about. And you construct an array where these pulsars provide very accurate clock timing measurements, which allows you to look for correlations in the deviation caused by gravitational waves. Why I'm briefly mentioning about pulsar timing arrays is because I think by now about a year ago, they announced to have found strong evidence for a gravitational wave background. So it's not yet the golden 5 sigma level, but they are hitting the 3 sigma plus level. So in 2020, there was a first hint of a signal by several of the pulsar timing arrays, but you would expect a certain spatial correlation between all these pulsars, as it's a homogeneous signal propagating past all these pulsar timing arrays. And these correlations were missing at that time. But then, so it has this kind of curvy shape if you look across the angular distribution across the sky, which is called the Heldings-Downs correlation. But then in 2023, a bunch of the pulsar timing arrays all announced strong evidence in the 2, 3, 4 sigma range, with also being consistent with the spatial correlations as shown here on the right-hand side. And so the Chinese pulsar timing array has about 4.6 nanograph, 3 to 4 sigma, European and Indian PTA about 3 sigma, and the Parkes pulsar timing array 2 sigma. So very likely, even if we just combine all these signals, even though there is some overlap between pulsars, they are quite complementary. The signal should already most likely hit the 5 plus sigma, which is underway. And otherwise, by integrating over longer times, the signal should be more clear and is quite exciting. At the moment, it's very unclear what it is. It's both consistent with astrophysical signals, which would be supermassive black holes colliding, as well as a wide variety of cosmological models and signals which could produce similar backgrounds. So in the future, we will learn more about this exciting signal, but now I will switch back. If you're interested, there is a very large list of publications going in all the details of all the different collaborations So yeah, have a look at some of those if you're interested. But now we'll switch back to Earth-based detectors on which my own work mainly focused. So the issue with the gravitational wave background is it's a very faint signal. And so we need to correlate data from multiple detectors because otherwise our signal is just buried beneath the noise. And hopefully, normally, the astrophysical background, which is the superposition of all these binary neutron stars and binary black holes, which are too weak to individually observe, but they're like incoherent superposition, should be observable by the end of this decade, as here indicated in the teal curve. And so in gray, I'm showing the sensitivity curve expected by LIGO, Virgo, Kagra at the end of their upgrades, somewhere later this decade. And then the different orange and blue curves are projected sensitivities for the Einstein telescope, which is a next generation detector planned in Europe. And so what we are measuring is strain, so the deformation of our Earth-based detectors. And if we correlate our two detectors, there is a component which is linked to our gravitational waves, which we are trying to measure. There is some correlation between gravitational waves and noise, but of course, both of them are uncorrelated, so we lose those terms. And then there is a term where the noise in one corresponding to the noise in one detector and noise in the other detector. And so if we assume this term to be zero, we can construct a statistic based on our strain measurements, which directly gives us information on the gravitational wave background we are trying to measure. And so I would say the past decades, typically, this assumption was, okay, it's zero, our detectors are thousands of kilometers away, we shouldn't really be bothered. But so my PhD exactly focused on what happens when is this not zero, and are there scenarios where we should worry this to be the case? There are some spectral artifacts where this is the case, but mainly magnetic noise is one of the more important issues, and I will go a little bit in more detail afterwards on that. But I also looked into seismic noise, mainly for closely collocated detectors, and then also how we can deal with this noise. And so what we've shown is that correlated noise could seriously limit future sensitivities or future searches as these noise sources start to couple more significantly to our detectors as we improve sensitivity. And so one way to think about this, so often the gravitational wave background is compared to the orchestra of the universe. So you don't hear all the different instruments separately, but you hear the symphony of the universe. And so uncorrelated noise would be that at two detectors, you have a construction worker working, but obviously there are different construction workers. And if you correlate your data, you just hear the combined symphony of the universe. But then if you're playing advocate of the devil and you have a cloned construction worker which creates identical noise at both detectors, what you will hear is just a horrible mess. And so will this occur is the question when we correlate data. Okay, we have our correlated noise. So first we need to understand what the potential noise sources are, as well as what their coupling mechanisms are. And so once we have this information, we can project their impact on our searches. If there is no effect, great, we can keep on doing amazing science. If there is, we need to do a little bit more work to try and mitigate it either at a hardware or software level. And if we fail to do so, we might end up where we have limited science, which hopefully is not the case. And so going into the magnetic noise example. So across the globe, there are thousands and thousands of lightning strikes happening every second. And these create electromagnetic fields. And this produces a standing electromagnetic wave known as the Schumann resonances, which is quite homogeneous and isotropic across the entire globe, which means it's correlated over thousands of kilometers. And so here are the three dominant lightning strike regions, mainly fueling or injecting energy in this electromagnetic standing wave. And so here on the right-hand side, I'm showing the coherence, where in blue, yellowish, and orange is correlation between magnetic sensors at the LIGO Hanford, LIGO Livingston, and Virgo sites, so thousands of kilometers away. And if we integrate over months to a year of data, we see in this low region there is a lot of significant coherence, but also up until almost 1 kilohertz, we remain to see coherence. So if we look at the strength of this magnetic noise, so this here in low frequency, these nice resonances, that's exactly the Schumann resonances. So it's these standing waves in the cavity formed by the Earth's surface and the ionosphere, which is fueled by these lightning strikes. And then what we noticed here at higher frequencies, this is linked to a superposition of correlated lightning strikes. So to some extent, it's really like a gravitational wave background, but instead of being the signal of gravitational waves being superimposed, it's like all these individual lightning strikes which are superimposed. And if you're measuring sensitive enough or long enough, these also create this kind of incoherent correlated background. So to give you a sense, like the scales we're talking about, it's picotesla, which is like roughly 1 billionth of the strength of your fridge magnet. So it are tiny effects, but the gravitational waves we're trying to measure, it's like deformations on the order 10 to the minus 24, 10 to the minus 25. So we have these extremely sensitive instruments. And so we're trying to understand whether these tiny fluctuations in your magnetic field are having an impact. So to get a sense how magnetic fields couple, what we do is we create strong magnetic fields ourselves inside our experimental buildings. So here you see the central building for the Virgo detector. And so what we've done here is in one of the corners, we've installed this giant coil, about 4.5 meters square shape, so quite massive. And so we put a current to it, and then we observe the exact effect of the magnetic field we generate ourselves inside the building. And so in the past, there was a much smaller coil, about a 1 meter diameter. But this one allows us to be much more precise and really do broadband injections rather than just separate frequencies as shown here. And so all curves apart from the two bottom ones are observed in the central building, so where the laser arms start, across a wide variety of modes. And so what I'm showing here is the magnetic coupling in meter over Tesla. So how strong a 1 Tesla field pushes our mirrors, or the equivalent motion. Of course, the fields are not Tesla, that's picotesla, but our mirror is also not moving meters, but like 10 to the minus 24 order. And so what's happening here in the low frequency regime, this coupling is really linked to the fact, so Virgo has tiny magnets attached to the mirror because we want to control our mirror such that we can align our instrument properly and know its position. But it also means there is a tiny error margin for these very weak magnetic fields to push our mirrors really and introduce some bias in our measurements. And so that's what we are seeing here. And at higher frequencies, it's a more complex combination of coupling through signal cables or physically vibrating other parts of the experiment, which then can introduce different noise sources, etc. So I talked about what a potential noise source is, what its coupling mechanism is, and so now I will look to projected impact on our searches to try and understand whether we should worry about it or not. And so we can do this by just combining our coupling function and our observed magnetic effects. And so what I'm showing here is so the stray noise for the Virgo detector, where in black it was the sensitivity during O3. And in blue, different projections depending on the magnitude of the magnetic noise. So if we zoom in around the 50 hertz, which is the power mains in Europe, you see that very close to 50 hertz, there are already tiny regions which were contaminated during data taking in 2020. But at the same time, also, if you look at projected sensitivities for subsequent runs, there will be regions which will take more contamination of this magnetic noise. So this is really an effect on the direct amplitude spectral amplitude spectral density of one single interferometer. But then if we go back to the story of the gravitational wave background, where we correlate our multiple detectors to try and dig below the noise of any individual detector, it also means we are much more sensitive to noise sources given that they are correlated. And so for most noise sources, this is not the case, but for our magnetic scenario, this will be the case, and we should also worry whether there is any impact there. And so instead of trying to construct a statistic which gives us an indication of the strength of our gravitational wave field, we're doing the equivalent, but for the magnetic field. And so we have our correlated magnetic signal component, and then we just need to multiply it with our coupling functions for our two detectors to get an estimate. So I discussed the coupling functions a little bit earlier and also showed the magnetic noise we have. And so if we fold in some other parameters which arise through to the analysis methods, we end up at this projection. So again, we have the energy density in our gravitational wave background, the quantity we're trying to measure. And so black is the sensitivity we achieved during the third observing run with LIGO and Virgo. And this is really a narrowband sensitivity across frequencies. But the gravitational wave background signals we are typically looking for are very broadband in frequency. Typically, it's like a power law-like behavior we're looking for. And so what we often do is construct a power law integrated sensitivity curve where we integrate over our frequencies to get a sense of how sensitive we are for these broadband signals. And that's this red curve. So any power law which is tangent to this red curve, we would be able to observe with 2 sigma significance. And so the purple is our magnetic projection, which is well below our reach sensitivity in R3. So there was no magnetic contamination, which we confirmed as well because we didn't see any signal. But then if we look at the projections for the design sensitivity, which should be reached later this decade, we see that both in the lower frequency ranges up until 50-ish hertz, as well in the hundreds and hertz above, there is risk of magnetic noise contamination at the 2-3 sigma level, depending where you're looking at. And that's quite worrisome because definitely here at the low frequency end, that's the region where we expect quite some signals to be visible. So we want to understand that better. I briefly already touched upon the Einstein telescope, and I have a couple of more slides on this. So LIGO, Virgo, Kagra are the current detectors. They're doing a great job. They're detecting tens of events, or a handful of events every week now, and so hundreds of events over one observing room. The Einstein telescope aims to improve the sensitivity by about a factor 10 in the strain sensitivity of the detector arms, which means that from a handful of detections every week, you go to detections every second, and all your signals starts to overlap, which brings its own problems with itself. But it basically will allow us to see almost all-to-all binary black holes and binary neutrino stars in the visible universe. So it's really dramatically upscaling sensitivities. And also for gravitational wave backgrounds, it really opens quite a lot of parameter space to look for as well astrophysical, but definitely cosmological signals, which are expected to be quite a bit weaker. So we also made a projection how magnetic noise can affect our detector there. But as it's still under design and not yet constructed, we went the other way around and we said, like, okay, let's assume we want our detector not to be affected by magnetic noise. How should our magnetic coupling function look like? And so we're trying to estimate an upper limit of the magnetic coupling function, where typically we want noise sources which are considered to be non-fundamental for the detector, such as environmental noise. We want them typically to be 1/10 of the sensitivity because there are hundreds of them. And so if you start adding all of those noise sources together, they shouldn't be too loud. Then we have the projected sensitivity of the Einstein telescope, which I briefly showed earlier. And then we have our magnetic noise component, which are the Schumann resonances. And so if we combine all of this, we can make predictions for what the magnetic coupling function should be, which is the yellow dot dashed line for the amplitude spectral density sensitivity for the Einstein telescope. And we can also do the same when we look at our correlated noise for a gravitational wave background or a correlated signal. And so these small dots, big dots, and stars are the current magnetic coupling functions we observe at LIGO Livingston, LIGO Hanford, and Virgo. So you see in high frequency range, definitely our amplitude spectral density of a single interferometer, we shouldn't really worry too much for the gravitational wave background, depending on which coupling functions you would take. But here in this low frequency regime, we're really orders of magnitudes off from what current detectors have. And so indeed, one of the big efforts for the Einstein telescope is to push to lower frequencies, because this would mean, so now we see a binary neutron star merging in an order of maybe 1 minute in our detector. But if you push to much lower frequencies, this 1 minute becomes a couple of hours. And so you can start to observe a signal of your merging neutron stars well before they actually merged. And then you can say to optical telescopes, I know in 10 minutes, a neutron star merger will show up there in the sky, look over there, and we try to do some multi-messenger astronomy. So if we will be able to pull that off, it will be very interesting, but we should be very careful about magnetic noise because there is definitely a significant reduction needed such that we can achieve the sensitivities we hope to achieve. Okay, the same result, but shown in a different way. How many orders of magnitude improvement do we need? And it's about 2 to 3 orders of magnitude in the lowest frequency regime. And so here I'm comparing 2 different designs of the Einstein telescope, one where we only focus on the high frequencies, and then the other one where we go to a cryogenic detector, trying to push the lowest frequencies and get these longer merger times. But this graph kind of shows that, because only here your sensitivities start to become comparable. This shows that, so this low frequency cryogenic detector is quite expensive and also quite challenging technology. But if you don't properly control your magnetic noise, the gain will be relatively small because your low frequency regime will be dominated by magnetic noise anyway in both scenarios at the low frequencies. And so again, that was individual detector sensitivities. So what happens when we look at our gravitational wave background? Again, we place upper limits on what the coupling function should look like, and kind of already showed the results a couple of slides back. But basically it means our sensitivity goes up a factor 10. So we should reduce the coupling function by another factor 10 compared to the previous results. And so we're really stuck here with a massive gap between the sensitivities we would like to achieve, but the magnetic noise contamination, which is really dominant. And so we should significantly improve magnetic coupling function compared to what we have in current day detectors. Yes, and so at high frequency, we don't really need a lot of improvement. Okay, maybe factor 5-ish, depending on which detector you look at, but like Hanford Livingston, which have the lower coupling functions, are pretty much exactly at our target sensitivity. But in the low frequency range, where we expect also more signals to be observable, we need to reduce our magnetic noise. So coming back to this diagram, so in which scenario are we? Are we here in the limited science case? And so I would argue we're still at this step. right? So our detector isn't built yet, and we can still try to do something to improve it. And I would argue that one of the better ways for the Einstein telescope to go forward is to try and minimize the noise at the hardware level. You always can do something at your analysis stage, but we're talking about 3-4 orders of magnitude. So anything you can already reduce at the hardware level would be a great effort. So trying to shield your detectors, use, for instance, optical fibers, and really carefully think about every step of your design and minimize coupling of magnetic fields at all these different stages. And if there is anything left, do some more work at the analysis stage as well. Yes. So to come to a conclusion. So here on the left-hand side, I'm showing the current LIGO sensitivities, as well as in green, the Einstein telescope, and in pink, Cosmic Explorer, which is also a next generation detector, but the US proposal, which doesn't push as much to the low frequencies, but is slightly better here in the bucket. So about a factor 10 improvement in your stray noise. And so this factor 10 here, because your volume you're probing explodes dramatically, it means that if you're looking at binary black holes here on the higher end of the total source mass frame, or binary neutron stars here at the lower end, you really go much farther into redshift. And for the black holes, you're even probing so far that you don't even expect any black holes from astrophysical origin to be there. And so if you would observe any black holes merging that far back in history, it's really strong evidence for primordial black holes as well. So very exciting. So there is definitely a bright future ahead for Earth-based gravitational wave detectors already this decade with LIGO, Virgo, Acra, significantly ramping up their sensitivities and increasing their detection potential, but also with the Einstein telescope. But we definitely should be very careful about correlated noise, and that it shouldn't limit our searches, definitely when we think about this gravitational wave background, where we try to look for these very weak signals. And so one very, very funny part, so one of my thesis supervisors, Nelson, when he did his PhD a couple of decades ago, he wrote, "Coherent noise sources for two detectors separated by thousands of kilometers seems unlikely, but is not completely excluded." And so now, a couple of decades later, we're reaching the area where we know it's going to bother us very soon. And so we really should start thinking about solving this problem and improving our detectors such that we are not bothered with this and we can keep doing amazing science. And that's it.
Time for questions. Maybe we start in the room and then in Zoom. We're gonna start it. Like, how would you, what parts of the design impact the magnetic coupling?
Yes. So when we look here, so at low frequencies, decoupling here. So Virgo has magnets attached to the mirrors. And so even though it's a quadrupole configuration, it's not perfect. And so you have magnetic fields directly pushing your mirrors. What LIGO detectors have is they don't have any magnets attached here, but they use electrostatic actuation. And the first ferromagnetic components are one stage up. And so with every stage you gain, you get a factor f to the -2 reduction. And that's why if you look here. So the Virgo coupling function is relatively flat, whereas the LIGO ones drop much sooner. So one way would be to make your design such that there's nothing ferromagnetic on your mirror, not a stage up, but try to even push it one stage further. But it also would mean it's much harder for you to control your instrument. So that's one issue. And another one is shielding. So the vacuum system already provides quite a bit of shielding, but you could think adding more layers or mu metal shielding, really trying to reduce the coupling. But again, it's very low frequencies, so it's extremely hard to shield for those low frequencies. But that would be a couple of ways to go about it, I would say. So probably with shielding, you're not going to get the full 4 orders of magnitude, right? Unless you spend absurd amounts of money on it. But if you can already gain 1 or 2 orders of magnitude, it makes quite a big difference, I would say. Because definitely it's like a steeply increasing function, right? If you gain 1 order of magnitude, you go maybe from like 15 hertz to 8 hertz or something like that, which definitely makes a big difference for the length of your signals, etc.
Would you say this is like, I imagine there are many challenges for the new
Yeah.
instrument.
Yes.
Where is it like up there with the top ones? What other big challenges?
So another big one is Newtonian noise. So what you have is like, if you have seismic waves, etc., they cause density changes in the soil, etc. And these density changes really push and pull your mirror. Because, yeah, it's a different gravitational wave field sensed by your mirror. And the issue there is you can't really shield it unless you have 0 mass around your detector, which is unfeasible. So that's also a big one. For instance, the Einstein telescope will be built underground because ground does decrease your seismic noise and it improves it. But still, it's about at least a factor 3 above the projected sensitivity. And so there they hope to gain that additional factor 3 by having a wide range of seismic sensors in a 3D configuration to then subtract your noise afterwards. So it's another solution indeed to have a extensive configuration of witness sensors to then try and do noise subtraction. But again, it's not going to give you orders of magnitude. It's like a factor 3 is already quite optimistic. And then we're talking about tens of sensors placed around. And as it has to be a 3D configuration, you need to have boreholes everywhere, which becomes quite expensive very quickly. Yes.
What's the timeline for the Einstein telescope?
So depending on when you ask it, it keeps moving back. So we're definitely getting close there. I think now it's like 2030, start digging, 2035, first starting up the instrument. So there are still 2 candidate sites, dirt hidden.
Where is it going to be?
Yeah, so one is in my hometown background. So it's Belgium, Netherlands, Germany. So it's a, I can maybe pull up one of my backup slides. So the baseline configuration currently for the Einstein telescope is a triangle with 3 Nusselt interferometers, which has some advantages, also some disadvantages, about 100-ish meters below ground. So Belgium, Netherlands, Germany is one of the candidate sites, and then the other one is Sardinia in Italy. I think by the end of this year, probably maybe early next year, they should make the final decision.
Is this based on politics, or is it based on seismic, the site, or what's the?
A very political question. A bit of both, I would say. So there have been extensive site investigations at both sites. There is also recently a 3rd candidate site in Germany itself. So roughly comparable, the sites are quite similar on order of magnitudes. That's in some fronts, one is better than the other. But I think in the end, it will be which country has the most money and is willing to put it on the table. But so quite of the participating countries already made preliminary budgetary funds available. And so we are on the S3 roadmap from the European Union, which then increases the odds of getting funds later down the line. So it's definitely in the stage where a lot of things is happening at a rather quick pace. Even a quick pace in academia is still spread out over quite some years. So I think like probably 25, we should at latest know the sites, 26, really start getting the money at all. It's order 2 billion euros. At least it was 10 years ago, so by now probably it's
Cheap compared to the LHC.
Yes.
Yeah, everything is.
Not everything, but
So yeah. But so even if there's magnetic noise and a lot of other stuff still hampering us, it still is an extraordinary instrument in of itself. But obviously, we want to get the maximum out of every euro we put into it to make it even more exciting.
Can I just, going back a few questions?
Yes.
You said putting it on a different stage?
Yeah,
I
so
didn't quite understand what you meant by that.
so here you have,
Oh, I
you
see.
have the mirror, which is like reflecting your laser light, and you test mass, which is sensitive to your gravitational waves. But if you don't do anything, you would just see seismic vibrations. So what you do is you make it a multi-stage pendulum, which with each stage reduces your seismic noise. And so typically we're talking about 4 stages of pendulum, multiple meters high. So for the Einstein telescope, it will be even quite a bit more, or otherwise more advanced techniques. And so with every stage, you gain a factor F-2 reduction. And so that's why seismic noise, it still limits you like at where your sensitivity curves for LIGO Virgo, they always go steeply upwards in a low frequency. That's your seismic noise boundary limit by your suspensions. But so if your magnetic noise is directly pushing your mirror, you don't gain any additional suppression from these suspensions. You gain suppression from the vacuum system and a lot of other factors. So if you can make the coupling go upwards as well, you gain additional coupling just by the physical seismic suspension.
Tara has a question.
Yeah, so I was reading a bit about the stochastic gravitational wave background.
Yeah.
And I was wondering, I know getting something like the CMB is a bit of a crazy dream.
Yes.
But how could an instrument like this help with maybe getting some science about the early universe?
So if there were some initial gravitational wave ripples from inflation, really, they are quite limited by our Planck measurements of the CMB. And so if you have a standard cosmological model, the blue curve is what inflation would show you. And it's like order 10⁻⁶, where we're trying to measure here. So like this is LIGO Virgo, Einstein telescope will maybe push up until 10⁻12, but we're still way off LISA at pulsar timing arrays as well. But then there are some alternative inflationary models which could make this background increase a little bit. And then there is some hopes of seeing it. If it's standard inflation, we basically have no hope to see it in anywhere the next centuries, probably, if we would even ever reach that sensitivity. But then there are a vast majority of other early universe processes we could probe. One, for instance, which Lisa or Lisa could probe is when there are first order phase transitions at the electroweak scale. They would show up in their main sensitivity region. And so it gives a nice complementary way to probe some particle physics models, which you cannot probe at particle accelerators because you're just looking at different energy scales, etc. And so it offers quite some nice different look in some of these early universe things. But also just like being able to look so much back in time, even for astrophysical sources, could quite revolutionize our knowledge because it's very hard to get light information or lots of information from visible matter from that early. And another one of the holy grails, if it would ever exist, are primordial black holes. And so being able to look that far back in time would be interesting. And another method to look for primordial black holes is to look for black holes with less than 1 solar mass, because your neutron stars wouldn't be able to form and in those mass ranges as far as we know. Neither your black holes. So if we see anything there, either it's primordial black holes or it's even something else quite exotic. So that's already being searched for with LIGO Virgo camera, and would be quite interesting if we could see something like that. And I think already now at the astrophysical level, there have been several black holes / neutron stars observed in gaps of the mass range where from traditional stellar evolution, you wouldn't really expect any objects to sit, which is still ambiguous what they are neutron stars, are black holes, we don't really know. But it already starts to indicate that our stellar evolution models, etc., aren't perfect, and we should look further to improve those.
Are there any questions online? Feel free to just unmute and ask.
Actually, who we can.
So maybe we end it here, and there's other questions. So again,